Greetings, this is Shannon Magic-Myers coming at you live from San Diego, California. Today we will be looking at testing a claim about the difference between two population proportions. Let's call them P1 and P2. Sometimes we're interested in whether two proportions are significantly different or in constructing a confidence interval estimate for the difference between two population proportions. The concepts are very similar to, working with one sample, except that you'll have two of each parameter and statistic relating to each sample and population. Previously, we were working with an example relating to the proportion of Maricosta to college students who vape. For this section, let's extend this scenario to include the proportion of students from Palomar College who vape. But first, as always, some essential ingredients. Notation, all right? So notation for two proportions. P1 is the population proportion for population 1 . X1 is the number of successes from the sample drawn from population 1. P hat 1 is the number of successes from sample 1 over the sample size of sample 1. So I'm filling that in. Sample size of the sample from population 1. And Q hat 1 would be 1 minus P hat 1. And so P2, N2, X2, P hat 2, and Q hat 2 apply to population 2. Now the standard error for the difference between these two proportions is just put an equals here, the square root of. Now if you remember, the standard error for just one sample was P hat Q hat over N. So now that we have two, we're going to put that standard error for the first sample proportion plus the standard error for the second sample proportion. There is such thing as pooling the standard errors to make this new standard error, but we're not going to do that in this class. It's easy enough to learn how to do as long as you have these basics. Groovy? Okay, and then the confidence interval estimate is just going to be P hat 1 minus P hat 2, that quantity plus or minus Z star, which will be determined by your confidence level, and that's multiplied to the standard error of P hat 1 minus P hat 2, which we found above. And then the Z value, okay, for this hypothesis test, P1 minus P2 equal to 0. Now notice that those P's do not have hats. That's what, for each of the confidence interval and this test, that's the population proportion they're talking about. So this one is z is equal to p hat 1 minus p hat 2 minus 0. Some textbooks are going to put minus quantity p1 minus p2, but since we're assuming that to be 0 under the null, we're not going to worry about that. And that's divided by the standard error of the difference between p hat 1 and p hat 2. All right, so just as a reminder, the standard error is this expression here. And so that's what you would plug into the standard error for these two deals. All right, groovy. So moving on, the requirements. So the sample data are from 2 simple random samples that are independent, okay? So we're not looking at paired data in this case, we're looking at independent samples. And for each of the 2 samples, right, like I was saying before, some people say that, you know, your number of successes and your number of failures need to be greater than 10. So it just sort of depends on what you're looking at. We'll go ahead and say that since we have 2 samples, I'll say Ni times P hat I has to be greater than 5, and Ni times Q hat I has to be greater than 5. But remember, some people replace that 5 with 10. The higher the number, the better it will be. All right. And this, of course, would be for I equal to 1 and 2 because we have 2 samples. Groovy? All right. So when testing a claim about 2 population proportions, the null hypothesis is that the difference of the 2 proportions is 0. And the decision to reject or fail to reject the null will be based on the null hypothesis of P1 minus P2 equal to 0 versus the alternative, which is P1 minus P2 is not equal to 0. So you're always going to have a two-tailed test. So you reject the null if your test statistic falls in the critical region. I've been calling it, I think, the rejection region, set by plus or minus z star. It's plus or minus because it's two-tailed, right? Two-tailed test, which is determined by the alpha level. The p-value method means that we reject the null if the probability of obtaining a test statistic at least as extreme is less than the alpha level. Confidence interval method. So you reject the null if the interval of likely difference values includes 0, because that would mean there'd be no difference between the proportions. Example 1, you think that the proportion of MiraCosta College students who vape is different than the proportion of Palomar College students who vape. During the fall 2018 semester, you decide to check it out. In a simple random sample of 80 MiraCosta College students, 18 of the students surveyed indicated that they vaped. In a simple random sample of 60 Palomar College students, 14 of the students surveyed indicated they vaped. Now, I'm going to add on to here that assume the 2 samples are independent, because there is overlap in the students attending the two schools. So we'll just put this in here. You would want to make sure that you didn't have any overlap where, you know, you have students that attend both schools if you were doing a study. First, let's start out by, finding out what the 95% confidence interval estimate for the difference between the proportions of students who vape at the two colleges is. We'll do it somewhat by hand, and then we'll use the graphing calculator to check it out as well. So let's kind of make a list. In the pink, I'll represent the first sample, which is the Maricosta College students. And so here's the info from Maricosta College. So call this one population 1. So in this population, N1 is what? Good, 80. And then successes, which is X1, perfect, is 18. And so from this information, what do we get? We can get P hat 1 is X1 over N1, which would be 18 over 80. And it turns out that that's exactly equal to 225 hundredths. And then population 2 will be the Palomar College sample. And so for population 2, we have N2 is equal to, beautiful, 60. And X2 is awesome, 14. So P hat 2 is going to be great, 14 over 60. And that turns out to be approximately 0.233. And one thing I forgot to do up top, we'll come back and do that, is to get Q hat 1. So let's do Q hat 2 right here. Remember, that's 1 minus P hat 2, which will end up being, let's see, 1 minus 0.233 is 0. And that's approximate as well, 0.767. And then P hat 1, or Q hat 1 rather, will end up being equal to 1 minus P hat 1, which will be 0.775. Groovy? Awesome. All right, so what else did we need to find? We also needed to find some computations, right? I think we needed to find the standard error for the difference between the two proportions, and we need to find the difference between the two proportions. P hat 1 minus P hat 2 is going to be, let's see, I'll do them in the same colors. So 0.225 minus 0.233, and it turns out that that is equal to, and again, this will be approximate because of the 0.233 is rounded, and that ends up being equal to about negative 0.008. Groovy? And we also need to find the standard error of this difference between the two sample proportions. And so that's going to equal to, remember, the square root of P hat 1, Q hat 1 over N1 plus P hat 2, Q hat 2 over N2. And so that will be approximately the square root of 0.225 times 0.775 over 80 and then this will go further over and we'll get the information from population 2, and so that's 0.233 times 0.767 over 60. And then that will be equal to, when I do this on the calculator, just be careful how you enter it in, that you get the correct value, but you want to make sure that you use the right grouping symbols. So let's just do this one together, second square root. I'm going to start parentheses, so we have 0.225. Since I'm multiplying, I don't have to put another parenthesis before I do the division on this first one. So times 0.775, and then I'm going to divide by 80, and I'm ending those parentheses. Technically on this calculator, it would do it correctly on its own, but just always be careful, err on the side of, extra parentheses if you need to. So then we'll have 0.233 times 0.767 divided by 60. Oops, that didn't turn out right. Okay, and then enter, and we get approximately 0.072. Groovy. All right, so here we go. We've got everything except for, great, Z star. So Z star is going to equal to what? We're doing a confidence interval, which is 2 tails, right? And it's the 95% level of confidence. So this would be Z alpha over 2, but alpha is good, 0.05. And so we would get Z of 0.025. Well, what does that mean? Z sub 0.025 means that we're looking for the z-score that corresponds to a cumulative area of 0.975 on the standard normal distribution. So coming back to our calculator, let's go to second distribution, and then we're going to go to inverse normal, remember? And the area we're interested in is 0.975, and that's all we have to enter because we're using the standard normal. So that's about 1.96. So now we have all of our pieces, all right? Isn't that exciting? So this is kind of all of our prep work. And now we can go to doing our confidence interval. So I'll just kind of divide this so it doesn't look too messy. And let's get to work. So remember that the general formula for the confidence interval is our p hat 1 minus p hat 2, that quantity, plus or minus z star times the standard error of the difference between the sample proportions. And we found all that information. That's the best part. So remember, p hat 1 minus p hat 2 is negative 0.008. And then that'll be plus or minus z star, which was 1.96, times the standard error of the difference between the sample proportions, which was 0.072 approximately. So let's see where we got these values. the standard error was that formula there, and that was equal to the 0.072. And then our Z star is the 1.96, and we got this over here, doing this work here. And then we also have our p hat 1 minus p hat 2 was negative 0.008. That's one nice thing about getting everything you need right away. Okay, so when you do this, this product over here, we will end up getting, so these are all equivalent, equals negative 0.008 plus or minus 0.141, giving us the interval of, when I subtract 0.141 from negative 0.008, I will get negative 0.149. That's got to be less than the difference between the actual population proportions. And then when I add the 0.141 to the negative 0.008, I get positive 0.133. So that is the confidence interval estimate, the interval of likely values of the difference between the two population proportions, right? So let's put that in words. So it looks like the 95% confidence interval estimate of the difference between the proportion of MiraCosta College students, who vape and the Palomar College students who vape. Falls between negative 0.149 and 0.133. Cool? This would be the result here. Good so far? Awesome. Sorry, that's squished a little bit in there. There we go. All right, so now let's take a look at doing the 5% level hypothesis test. Now remember, this is a two-tailed test. So at the 5% level of testing, that's going to correspond to the 95% confidence interval estimate. So we'll be able to come back and use this confidence interval in a conclusion for the hypothesis test at the end, all right? So let's state the null and alternative hypotheses. So remember that our null is that there's no difference between these population proportions. So if there's no difference, then it means that P1 minus P2 would be 0. Versus the alternative, which would be that P1 minus P2 is not equal to 0. And so that is, the basis of our test. And this not equal tells us that it's a two-tailed test, right? All right. So let's go ahead and find the test statistics, because you need the test stat for both the critical value and the p-value methods. So the test stat, remember, the general formula was z equals p hat 1 minus p hat 2 minus 0, because we're assuming p1 minus p2 to be 0, all over the standard error of p hat 1 minus p hat 2. And remember, we found all that stuff already. So we will get that z is equal to, remember that p hat 1 minus p hat 2, we found that to be good, negative 0.008. If you take away 0 from that, you still get negative 0.008. And then the standard error we found before to be beautiful, 0.072. So just so you remember where we got those from, this was our p hat 1 minus p hat 2. And then this right here in the denominator is the standard error for that difference. All right, and so when we approximate this, we'll get z is approximately, it's actually all approximate, it's approximately negative 0.12 to the nearest hundredth. Good so far? Awesome. All right, so continuing, we will go ahead and we'll just do all three methods. We've already started on the confidence interval method. We'll include that conclusion for the test in our overall conclusion. So the critical value method, remember, you need to find your z star. So we need to find z star, and since it's a two-tailed test, right, we need to use half of our alpha level, right? So we already found that that's going to be z of alpha over 2, right? Well, z alpha over 2 is 0.05, z 0.05 over 2, which in turn is z of 0.025. Well, we found that, remember, over here when we were doing this work. Cool so far? I'll go ahead and highlight so that you can find that. So our z of 0.025 is equal to 1.96 approximately. But we need to do plus or minus that because we have two tails. So two tails means we use plus or minus 1.96 to divide the z-axis into intervals. Groovy? All right, so the z star being 1.96 was what we had looked at just a minute ago. And so now 1.96 is really close to 2, right? So we'll call this z is 1.96, right? And over here, close to negative 2, that'll be z is negative 1.96. Remember, this is the z-axis. And so our rejection region will lie in these little tails right here. And so we need to utilize our test statistic and see if that falls into the shaded regions here. So our test statistic, if you recall, was this one here. So we found our test stat to be, I'll do that in yellow, I guess. Our test statistic was negative 0.12. So coming back here, if you go to negative 0.12, I mean, that's going to be about here, right? So Z is negative 0.12 is the test statistic. That Z-score for our test stat does not fall into either of the critical regions, so we fail to reject the null hypothesis. Good, good? All right. Now, the p-value method, we need our alpha level. So remember that alpha was equal to 0.05. And again, our test statistic was that Z was equal to negative 0.12. Now, with the p-value, we basically need to, I mean, if you look at negative 0.12, which we said was about right here, and we kind of separate that area, so that's Z is equal to negative 0.12. Again, this is our Z-axis. And so here, when you were using our p-value method, it's two tails, right? So you need to double that area. So here, we're going to find this area here. So we're going to find the area here, okay? Just like we did before all the hypothesis tests, we're finding the probability that Z is less than negative 0.12, but we have to double that, don't we? Because we're doing a two-tailed test, right? So here, we need to find, we're basically asking ourselves, is the probability that Z is less than negative 0.12. The reason why we're doing the less than is because our Z value was negative. If we had gotten a positive, we would have done it greater than. And we're doubling this, so it's 2 times this probability less than 0.05. So, well, 2 times, let's see what this probability is, and we want to know, is it less than 0.05, because that's our alpha level. We go to second distribution, and we have our Z value, so we go to our normal CDF, remember, and we are going to do this normal CDF of, it's a less than, so I'll just do a real big number for the lower bound, and then negative 0.12, and I can just go ahead and enter it because we're dealing with the standard normal, and that's about 0.4522. Well, if I double that value, I'll get 0.9044. Well, is that less than 0.05? Nope, not unless you've been drinking, right? So we fail to reject the null hypothesis. And that's fine, right? That just means that, hey, maybe, especially with a very large p-value like that, basically what that means is that, hey, we're I don't think we're on the right track here, or our sampling methodology is really bad. So you might want to look at some other interesting things. A lot of times we just do these studies to find out if they bear further study, right? Okay, so conclusion. You can see from parts A and B why we fail to reject the null, right? Let's take a look at our confidence interval estimate. Now the confidence interval estimate, do you see it does contain 0 because you have a negative on the left side of the inequality and a positive on the right side. Does that make sense? So 0 is a likely value. So just using, and the fact that this 95% level of confidence corresponds to a 5% alpha level hypothesis test if it is a two-tailed test, okay? And if you're wondering, you just draw the picture. Both of them, you'll see, will have 0.025 on either tail. So here, we would say there is not evidence at the 5% level to suggest that null hypothesis, which remember, the null hypothesis was that the population proportions were not different. Should be rejected, right? And then furthermore, the 95% confidence interval of likely differences contains 0 so it is reasonable to conclude that the proportions are not significantly different. Okay. Cool. All right. So now how would we do a hypothesis test on the graphing calculator? If you just go to Stat and you go to Test and you go to two proportion z-test. I entered in all the data, so x1 is 18, n1 is 80, and all that good stuff. And if you take a look, we drew one side of the probability. This is the picture of the t-test. With a test statistic of negative 0.12 approximately, the likelihood of getting another value at least as extreme is 0.91 about, which is very close to 1. So you're almost certain to get another value at least as extreme. So that's why we fail to reject the null hypothesis. So I pasted a few things in. Here we have this right here just shows you how we found the p-value, or at least half the p-value, the probability that z was less than negative 0.12 using the calculator, the normal CDF. And then down here, this was from when we did the confidence interval estimate. So all of these are screenshots, right, of what we did here, right? And then this relates to the test that we just did on the calculator, and all the good stuff here. All right, so that way you can see the screenshots as well. So I will talk to you soon. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. Bye.